Hey guys, we're going to start learning about magnetism. So before we begin, you should definitely have your notes packet printed out in front of you. Otherwise, it's going to be hard for you to write things down. And well, you can obviously read what's on the screen, but writing things down would be a little difficult without the actual physical paper. So the first little bit here is just symbols and units for magnetism. Kind of unaccountably, the symbol for magnetic fields is B. Not really sure why they picked that one, but B is always the symbol that they use for a magnetic field in any kind of an equation or a diagram or something like that. So if you see the letter B, it means there is a magnetic field, and then if they've got a bunch of, say, arrows next to it like this, then that's indicating the direction of the magnetic field. The unit for a magnetic field, there's two units. One is the Gauss, and the other is the Tesla. The Tesla is considered the standard unit for the magnetic field. And a Gauss is 1 times 10 to the negative 4th Teslas. Now, the reason why they even use Gauss is probably at least partially historical, but there's also the fact that Gausses are actually more reasonable. If you're talking about something like a refrigerator magnet, they are not reasonably measured in Teslas. Teslas are huge. A 1 Tesla magnet is not unreasonable. You may perhaps have held one if you've had one of those super strong rare earth magnets, right? That would be like a 1 Tesla magnet. But if you're talking about 10 Teslas, now you're getting into just outrageous territory. All right, next I thought we would take a look at some of these orders of magnitude for magnetic fields, mostly because it's kind of entertaining, all right? But also, to a certain extent, because it helps us to have an opportunity to talk about some of the big questions like where does a magnetic field come from. Some of these I think are maybe a little bit obscure and you might not be sure what they're referring to, but this one here, human brain magnetic field and strength of the Earth's magnetic field. Those ones I thought it would be a good idea to talk about because, I mean, you might be wondering, why do I have a magnetic field? Like, what the heck? The human brain has a magnetic field? That's a strange idea. And it is kind of a strange idea. What on earth would cause you to have a magnetic field? Well, if you've ever heard of an electromagnet, or if you heard them referred to in some video I had you watch previously on magnetism, electromagnets make magnetic fields by passing a current through a wire. So this is something that we're going to talk about a lot in a few days in this unit. But anytime you've got current flowing through a wire, there's actually going to be a magnetic field around it. Sort of hard to draw around, but imagine this being in front, and then the sort of loopy part goes behind it. Okay, so maybe if I draw it like that. Okay, so the magnetic field sort of circulates around this wire, right? And that's something we observe around anything that carries current. Well, your brain runs on electricity. All of those little neurons involve passing electric currents, which is the reason why you have a magnetic field, but also the reason why things like electricity can actually hurt you, is because your neurons run on electricity. So you could imagine that if you start passing electric current through your body, that might start messing around with your neurons. It's why you thrash when you're being electrocuted, and it's why it hurts when you get electrocuted. All right, now the Earth's magnetic field. The Earth's magnetic field is actually also due, sort of, to currents, although maybe not exactly. So a lot of the time, I know I thought this when I was in elementary school, people think, well, you know, if this is the Earth right here, and, you know, it's on a tilted axis and whatever, oh, and then the Earth has a magnetic field. It's because of the Earth's iron core. And see, there's like a huge, basically it's like there's a huge bar magnet down the middle of it. No, absolutely not. I know the Earth has a nickel iron core. That is a well-advertised fact that everybody knows. And it would be false to say that the iron core is unimportant in establishing the Earth's magnetic field. But in a literal sense, this is not right, okay? The Earth's core is actually too bloody hot for it to be a permanent magnet. You can actually destroy magnets by throwing them in the fire. I don't know if you knew that, but now you do. So all that information, that would make it be a magnet goes away if it's too hot. On the other hand, if you have molten ionic compounds and they are circulating around in various ways, as long as they're circulating around in the right way, what it will end up doing is being effectively a current, because if it's, say, I don't know, let's say ferric oxide. Ferric oxide is made of these ions right here, and if you have charges moving around, that's actually what's going on inside of a wire. You have charges moving around. If the current is this way, remember that means electrons are moving that way inside of the wire. And apparently, moving charges make magnetic fields around them. Okay, so if we have molten ferric oxide inside of the Earth's mantle and inner core circulating around in just the right way, it will make a magnetic field around the Earth. Okay, now, exactly how that works is actually pretty complicated and an open question in physics, but it is the established explanation that this is what's going on. It's called, here's a fantastic word for it, it's called magnetohydrodynamics. It's actually an inside joke in my house. Anytime you don't know the answer to how something works, and someone says, "Daddy, how does this work?" the correct answer is magnetohydrodynamics. Yeah, definitely go with that one, because there you go, it's like a $1 million word. All right, magnetohydrodynamics then is the reason why the Earth has a magnetic field, and your brain sort of for the same reason. Okay, now other things in this table. Strength used to levitate a frog. That one kind of jumps out at everybody every year. What in the world could that mean? And can I levitate using a magnetic field? Well, maybe sort of. So I did a quick search on YouTube for levitating frogs, and some of these videos explain what's going on with the frog. I'll just watch the 11-second one because we don't have time to listen to somebody else talk about it. But there he is, levitating in... What in the world is going on with that frog? Well, we aren't going to get into all of the science about how exactly that works. What you really need to know about how you levitate a frog is frogs contain water, and water is something that's called diamagnetic. And anything that's diamagnetic opposes all magnetic fields that are coming into it, meaning it creates its own magnetic field that opposes the entering magnetic field. So water being diamagnetic, you can use it in this particular way to levitate a frog. It takes a lot, 16 Teslas. All right, now other values in here. Strongest continuous magnetic field produced by, okay, all right, that's impressive. That's impressive because 1 Tesla, remember, is a crazy strong magnet. Okay, some of these other ones, we start to get into just absolute bonkers territory, okay? So this one is based on a very, very powerful electromagnet, right? We said a current makes a magnetic field. Well, you need a lot of current and arranged in a particular way. We'll talk about that more later on this unit, so that it makes a large magnetic field. Strongest pulsed magnetic field, so that would be like they turned on the current, and then they turned it off. Obtained, I love this qualifier, non-destructively. Okay, all right, so what about oh, look at this one. Destroying the used equipment, but not the laboratory itself. And then, of course, next line down, we have the Soviets. Okay, yep, since they apparently did not care about the laboratory, they just wanted the record. Well, good job, guys, you did it. All right, now these other ones, if you want to know why a neutron star or a magnetar, which is a special neutron star, has an enormous magnetic field, that would be a subject for a Google search because it involves talking about all kinds of things like exactly what's a neutron star made of. It's not just neutrons. And also things like superfluids, which I don't really want to get into. All right, next thingy is we need to be able to talk about, I mean, all that stuff is fun and nice and stuff, but what we need to be able to talk about is magnetic forces that act on charges. So there was a demonstration I used to be able to do with the old cathode ray tube TVs, where I would hold a magnet up to a cathode ray screen. There's a semblance of a TV. So, if I had this, magnet here, and I held it close to the screen, if the screen, say, originally had some sort of a image on it, say, I don't know, like a meep, all right? When I hold the magnet close to the screen, the meep gets really weird. Like, the colors get all warpy, and also the image is distorted and bent around, and it starts looking a little bit like a Picasso meep, if I'm lucky, if it's even recognizable. And the closer I move it, the weirder things get. Now, the reason for that is because of how the old cathode ray tube TVs work. What they had at the back of them was a cathode ray tube, and it would fire electrons at the screen, and those fast-moving electrons would hit little things called phosphors, and depending on the energy of that electron when it hit, it would excite the electrons in the phosphors to a different degree. And the degree to which they were excited correspond then to the color of light that they emitted. What that has to do with this is the following. Remember, we said moving charge makes a magnetic field. So that means if we've got an electron flying along here, right, that's moving charge. It has a magnetic field because it is moving charge, and moving charge makes a magnetic field. So if this thing has its own magnetic field due to the fact that it's moving, well then it will experience a force for sure due to a strong magnetic field, right? If it is a magnet, then it should interact with magnets, and therefore the screen gets distorted and weird things happen. All right, now how do we calculate that force? Well, the equation for the force is QV cross B. Mr. Erico, what do you mean cross? Well, I mean that right there. That looks like a multiplication x to me. Well, it's sort of like multiplication. So this formula right here involves what's called a cross product, which we'll get into in the next video. Let's just finish up by talking in this one about what the various letters stand for. So force, okay, got that one. This is charge in coulombs. All right, usually that's a pretty small number if you're talking about things like electrons and protons. This right here is the velocity. The direction of it matters, as we'll discuss. And then this would be the magnetic field measured in Teslas. Okay, so what you should be able to see from this formula is a couple of things. If the thing's not moving, if V equals 0, then the force equals 0. So you can only exert a force on a moving charge. Pretty cool. All right, more about this formula in the next video.